Kinetic theory of gases. Bernoulli's picture, dash. Daniel Bernoulli, in 1738, was the first to understand air pressure in terms of molecules. He visualized them shooting around very rapidly in a closed container, supporting a weight as shown by constantly bouncing off the underside of the piston. Given more room, they would rush in to fill the new space, just as a gas is observed to do. One-dimensional, one-molecule gas : the molecule round trips in time 2 liters/v, so it bounces off the piston. v/2 liters times per second, each time delivering momentum 2 mv, so the piston will pick up momentum from this gas at rate 2 mv x v/2 liters per second. Force from gas on piston. F equals rate of change of momentum equals mv2/L. An equal opposite force must be supplied from outside to keep the piston at rest. Molecule in a two-dimensional box, dash. Assume perfectly elastic collisions with all walls. The molecule will follow a zigzag path. The time between collisions with the same end, say the end at x equals L, is now 2 liters/Vx, and the momentum transferred per collision is 2 mvx, so the average force on the end is mvx 2/L. This will still hold good in 3 dimensions. N molecules in an LXLXL cube, dash. Assume first that we have a very large number n of molecules bouncing around, so small that they don't hit each other, each follows its own zigzag path. The force on the right-hand wall at x equals L is just the sum of the forces from each one, so F equals mvx1, 2/L plus mvx2, 2/L plus mvx3, 2/L plus mvxn, 2/L. The speed distribution, dash. Although the molecules fly freely almost all of the time, they do collide occasionally. Assuming random elastic collisions, there will be transfer of energy, typically of order kT, from one to another in a collision. The chances of a particular molecule picking up kT n times in a row is similar to the chances of a coin toss coming up heads n times in a row. That is, high energies are exponentially unlikely. Maxwell's speed distribution, dash. Maxwell did the math precisely, and found the probability of a molecule having a high energy at a given moment did drop exponentially with energy, meaning that for each extra kT of energy, the probability of finding a particle with that energy drops by 1/e 0.37 more than a factor of 2, because the average amount picked up per collision is less than kT. Maxwell's exact result is escaping from a planet, dash. Maxwell's speed distribution makes it quite easy to predict which gases can escape from planetary atmospheres. For the Earth, the escape equals 11 km per second. The upper atmosphere has parts as hot as 1000 K. The speed distribution includes where we've used. For H2, at 1000 K, the fraction of molecules at escape velocity is of order 10 to 6, for He 10 to 12, for O2 10 to 79. This means the H2 will escape almost instantly, the He pretty quickly, and the O2 never. Vapor pressure and humidity, dash. The H2O molecules in liquid water strongly attract each other, holding the liquid together. But these molecules are still jiggling around with a Maxwell speed distribution. This means a fraction of them near the surface are moving fast enough to escape, forming a vapor above the surface. In a closed container, with enough water present, an equilibrium situation is reached between escaping and returning molecules. Water and vapor in equilibrium, dash. In equilibrium in a closed container, the molecules in the vapor have the same average kinetic energy as the air molecules, so exert pressure on the walls of the container proportionate to their numbers. This is the saturated vapor pressure. It varies with temperature. Like E-AT, not surprising since its origin is molecules fast enough to escape. Water vapor pressure, dash. At room temperature, saturated vapor pressure is about 2.5% of atmospheric pressure. At 100 degrees Celsius, it equals atmospheric pressure. This means small bubbles formed in the liquid by fast-moving molecules coming together are no longer crushed by the surrounding atmospheric pressure. The water boils. In mountain resorts like Aspen, water boils at a lower temperature, producing inferior T relative humidity and dew point : If water is constantly boiled off in a closed room, it is not possible to establish an equilibrium situation with vapor pressure above the saturated value for that temperature. Further water will condense out on the walls, etc. At this point, relative humidity equals 100%. Relative humidity equals vapor pressure / saturated vapor pressure. Dew point, temperature at which dew forms, that is, water condenses out.